Okay, welcome to ELTN 132, Unit 3. I'm going to be talking a little bit about Boolean algebra here. I want to go over a few of the rules because some of the terminology, the first time you see this, it might look a little weird. So let's take a look at an example here of some of the rules with OR gates as examples. So one of the first ones here is this expression that says A or 0 equals A. And you think, what on earth does that mean? Well, what A is basically a placeholder. A can either equal 0 or A can equal 1. So either of those situations, in this case what it's saying is that if one of the inputs is low, no matter what the input is, whether it's a 0 or a 1, that value is copied to the output. So let's see if we can see what this looks like here, kind of from a circuit standpoint. Now, if A equals 0, that's the same thing as grounding the input. So that input is at 0 volts, which is equivalent of a 0. So if A is 0 here, we're certainly going to have a 0 output here. That's what this first one is representing. The second case is if A is 1, the output will be 1. Okay? So what this is really saying here is that anytime one of these inputs is 0, it's simply going to be A that's copied over. And really what that becomes, in a way, is just a wire. So that basically eliminates that gate. And we'll see the advantages of why this is important, where we're going to use this in minimizing circuits. Okay, let's take a look at another example here. Here we have A or A naught equals 1. Again, because that symbol, that plus symbol, represents ORing, we can draw this as an OR gate. And we have two inputs. But in this case, what it's really going to mean is that if A is 0, A naught is 1. Or if A is 1, A naught is 0. And in that case, in either of these situations, one of these inputs, either the top input or the bottom input, are going to be a 1, no matter what. So again, what that does is it forces it to be a 1 in that case. Okay, let's take a look at another example here where we have this expression A or A and B equals A. So what we can do on the left-hand side of this equation is eliminate or factor out this A term. Okay, if you remember back to algebra, this follows the same process. So we're going to look at this part of the expression, and we're going to factor out an A. And it's 1 or B. So anytime, however, that we have a 1 or some term, again, remember that ends up being a 1. Simply because anytime you have an OR gate, and if one of the inputs is always a 1, the output has to be 1. So what happens is that part of the term becomes a 1 there, and we have A and 1. And if we look at the rules of algebra, again, for Boolean algebra, A and 1 is simply reduced to A. And if we take a look at that, why that is if we have an AND gate here, and one input is 1, then if this input is 0, which we're calling A, the output is 0. Or if this input is a 1, this output is a 1. So it simply reduces, so this whole term on the left simply reduces to A. And that's what we end up with there. So that's an example of where we can factor out a variable in a Boolean equation. So in this case, what we can do, in an equation like this, we have A or B ANDed with A or C. Using the FOIL method, which if you remember back to algebra stands for first, outside, inside, last, we can group these terms together. So for example, the first term would be A and A. Outside would be A and C. Inside would be B and A. And last would be B and C. So we did the first, the outside, the inside there would be 3, and the last there would be 4. Hopefully that's not too confusing. Now, again, some of these terms, for example, if we have A and A, what happens is that term just simply becomes A. So we can rewrite this here, A or A and C, or B and A, or B and C. But pretty soon you can start to see other things that we can factor out. Remember this one here, A or AC? That becomes A and 1 or C, and that whole term ends up dropping out. Okay, so now we're left with A or BA or BC. Now, based on the commutative law, anytime we have a term like this, B and A, we can simply flip the terms. So we can rewrite this A or AB or BC. Excuse me. And once again, we can factor out an A here. A and 1 or B or BC. And this term goes away, and we're left finally with A or BC. So in that case, we actually used a few different rules here. We started by distributing all of these values to find out that we have 4 individual terms. And then if we group terms together that have common terms like A or A here, we can then further reduce it until we get to our final answer, A or BC. Okay, let's take a look at this last example here. One of the rules states that A or A naught and B is equal to A or B. Now, sometimes the proof for this is a little tricky, and so in this case what I'm going to do is simply draw out the logic circuit and see if we can kind of look at the logic circuit and understand how this works. So we have one input here that's A, and we're going to take that input and go into an OR gate here at the end. And we'll say the output is X, like we usually do. And then we're going to break off here and have our A naught term, but we're going to AND it with the B input. So these two are ANDed together, and then that AND output goes to our gate. So here's our equation. The OR gate here is simply the ORing of these two terms, A in this case, and then we have A naught and B. Now it's pretty easy to see if A is a 1 at any point, it forces the output to equal a 1 here. But the other part is a little confusing. We can see here that for this lower equation, A would have to be 0 and B would have to be 1 in order to have the other input. So one way to do this, to kind of examine it, is we can just draw a truth table here. 0, 0, 1, 1, 0, 1, 1. If A is 0 and B is 0, there's no way that we're going to have either of these outputs true, because we have to have a 1 here. So we can see that our output is 0 there. If B is true, if there's a 1 there and A is 0, what happens? Well, there's a 0 here, so that doesn't do anything. But the inverter converts that to a 1. Now we have a 1 here, so we'd have a 1 on our output there. That's because of the inversion of the A naught term. Let's take a look at the next case. If A is 1, doesn't matter what B is in this case, because that 1 is going to propagate through to the output here of our OR gate, all the way through in this direction. So that's a 1. And again, anytime A is 1, it doesn't matter if B is 0 here in this case, B can be a 0, but that 1 again is going to drive that input to the OR gate high, and our output is 1. So this truth table, if this is our X, if this is our output, this is the same as the OR function. Okay? And what basically this is saying is that in this case, this A naught term just basically falls out of the equation. Kind of an interesting one there.